So when looking at reaction mechanisms, we talked about how reactions are made up or can be made up of multiple steps, multiple elementary steps. And since different reactants are involved in different steps of those multi-step reactions, they can be involved in the rate determining step, they might be involved before that, they might be involved after it. Their concentration ends up having different effects on the overall rate of a chemical reaction. The way in which the concentration of a given reaction affects the overall reaction rate is called its reaction order. The order of each reactant in a chemical reaction must be determined experimentally. You cannot determine it just from looking at the stoichiometric equation. Orders of reaction can be integers or fractions, but for our consideration with DP chemistry, we're only going to look at whole number orders of reactions. And really, we're going to look at three, those that are called zero, first, and second order reactions. The orders of reaction do not have to match the coefficients of the stoichiometric chemical equation, but the orders for a specific reactant might match up its coefficients in a given rate determining step. Like within one elementary step of a mechanism, the coefficients on a reactant might match its order. And we'll look at that more closely with some examples. But again, the stoichiometric coefficients do not have to match the coefficients or the orders of reaction. So let me get into these orders. So there are three basic types of reactants that we're going to worry about. There are zero order, first order, and second order reactants. Zero order reactants are reactants whose concentration has no effect on the rate of a chemical reaction. I know that seems unlikely or illogical based on a simple consideration of collision theory, but we're going to look at how they might be involved in the reaction mechanism, and we'll see that this is actually quite possible. First order reactants are probably the ones that are the most simple, sort of matching what we would expect from a simple consideration of reactions in collision theory. First order reactants are reactants whose concentration has a directly proportional effect on the rate of reaction, meaning if I double the concentration of this reactant, it doubles the reaction rate. If I half the concentration, it halves the reaction rate. If I quadruple the concentration, it quadruples the reaction rate, and so on. There are also second order reactants, which are reactants whose concentration has a squared effect on the reaction rate, meaning if I double its concentration, the reaction rate quadruples. If I half its concentration, the reaction rate gets times by 1/4 or divided by 4. So the effect, it has a much greater effect on the reaction rate. And so there are a couple of graphs that you should be comfortable with. These are graphs here that show the effect of the concentration of a particular reactant. They're calling it reactant A in these examples. So this is the concentration of A in moles per dm cubed, and this is the reaction rate. Well, as we change the concentration of A, if it's zero order, there's no effect on the rate. So assuming all the other reactants in the reaction are staying at a constant concentration, no matter what we do to the concentration, there is zero effect on the rate. In this one, it's first order, so directly proportional. It should look just like a y equals x graph, whereas I increase the concentration, the rate increases by the same amount. And in the second order, the rate essentially looks like an x squared graph or a quadratic graph. Whatever I do to the concentration of A, then the rate should have that effect squared. So when I double the concentration, it goes up times 4. When I triple it, it goes up times 9. Quadruple it, goes up times 16. I think you know what a quadratic graph looks like. Another type of graph that you're supposed to be aware of and familiar with, but maybe not as intuitive, is what happens to how does the concentration of that reactant change over time? Now, these graphs are based on the other reactants being in great excess, which means that the concentrations of those other reactants basically doesn't really change significantly in the time period that we're looking at on these graphs. So the other reactants are staying basically constant in their concentration. So what happens to a particular reactant's concentration over time in a reaction? Well, if a reactant is zero order, that means it has no effect on the rate of the reaction. So it gets used up at a steady rate, assuming those other reactants have a constant concentration. So zero order reactants just get used up at this steady constant rate over time. First order reactants, though, they affect the reaction rate. So as they get used up and their concentration goes down, the rate of reaction also goes down by the same amount. So if you think about that, when you've used up half of the concentration of a first order reactant, now the rate is only going half as fast. So it's getting used up half as fast now. This ends up leading to what we call a constant half-life. A half-life is the time it takes to use up half of something. So it takes the same amount of time, if you look at this graph, so this is our initial, to get down to half, that's about half, forgive my roughness here, took that amount of time. Now to get down to a quarter, which is half of that, takes pretty much the same exact amount of time. To get down to 1/8 takes, it's about here, the same amount of time. So the amount of time that it takes to get for the concentration to half, from full to 1/2, from half to 1/4, from 1/4 to 1/8, and so on, always takes the same amount of time. This is going to be a really super important idea for these graph questions. They give you questions, especially like on paper 1, they'll give you graphs and expect you to be able to identify if it represents 0, first, or second order. And the first and second order, as we'll look at, they look very similar. They're both curves like this, decreasing at slower and slower rates. And the way you really have to figure it out is to look at which one is, can I tell, is sort of a constant half-life. So the time it takes to go from full concentration to half, half to quarter, half to eighth, that's a constant time interval. When you look at the second order, they drop much more steeply, and then they decrease really slowly after that. And that's because the change in the concentration has such a huge effect on reaction rate that they get used up quickly at first, and then once the concentration is lowered, the rate really slows down. And if you tried to do the same thing with the half-life here, we'd see the time to go from initial to half is, about this much time. And then time to go down to a quarter is a little bit longer than that. And then the time to go to an eighth is getting longer. And the time to go to 16th is getting longer. So the half-life keeps getting longer and longer in a second order because of how much the change in concentration is affecting the reaction rate. We end up putting all these orders of reaction together into something that's called the rate equation, or the rate law, or sometimes the rate expression. They all basically mean the same thing. It's a way of mathematically relating the rate of reaction, which we can get a mathematical value for, and the concentrations, which we can have mathematical values for. So the rate in here represents the rate of the reaction, which the technical definition has to do with change in concentration per change in time, usually seconds, but it could be any time unit. So we get moles per dm cubed per second, for example. The brackets in these equations represent concentration. So brackets around A means the concentration of A, therefore the units of any bracket is moles per dm cubed. X, Y, and Z up here, those are the orders of reaction with respect to each individual reaction. So a 0 order means an exponent of 0, first order means an exponent of 1, and second order means an exponent of 2. If you add all those exponents together, you get the sum of the orders of reactants, and that equals the overall order of a reaction. And K is something called the rate constant. The K is really just a value that's plugged in there so that we can mathematically equate the rate to the concentration. So it doesn't have too much of a meaning outside of that. It's really just, you kind of have to figure it out from the rate data, and it just makes the two sides of the equation equal. So it's got a different value for different reactions, and it also has a different value for different temperatures. So there's not one rate constant that's going to show up in the data booklet, for example. Its units actually also change based on the overall order of the reaction. So the units are basically there to cancel out all these concentrations so that overall the units on the right side of the equation are also equal to moles per dm cubed per time. So the units on both sides of the equation have to be the same, and we'll do practice with figuring out what the units of a rate constant are. Rate constants are constant for a given temperature. But if you increase the temperature, we know that the rate increases, and if we don't touch any of the concentrations, the only way to mathematically make that make sense is that with increasing temperature, the value of K must also go up. It doesn't affect K in a linear fashion. It affects it in a nonlinear fashion, which we'll look at more later on in the topic. But just know that temperature for you guys is the only factor you have to consider that affects the rate constant. and it does so in a nonlinear way, but increasing temperature increases the rate constant. So here's a specific example. If A were 0 order, B was 2nd order, and C was 1st order, the rate equation would look like this, except that since A to the 0 is just 1, we wouldn't normally write it, and we would get rate equals K, B squared, C to the 1st. The units of rate are always going to be moles dm minus 3, and we'll say seconds minus 1, since that's the most common unit of time that you'll see. So those are the units of rate. Well, if we're going to try to figure out what the units of the rate constant are, we have to look at how many times concentration was used on this side of the equation. I've got concentration squared, and I've got concentration to the 1st power. So really, I've got moles per dm cubed. I'll write it this way, and I've got that cubed, because I have to the 2nd and to the 1st. That means I've got, that's equal to moles cubed and dm to the 9th power on the bottom, or dm to the -9. All right, well, I'm trying to cancel these out, right? With K, I have to cancel these units in such a way that on both sides, I get moles per dm cubed per second. So when I see it, I've got too many moles on top by a factor of 2, and I've got too many dms on the bottom by a factor of 6, right? It's supposed to be dm3 on the bottom. So the units of the rate constant are really just there to cancel out the extra moles and dms in order to give us the same units as for the rate. So what I'm going to put is I must have moles squared on the bottom for the rate constant, because that will cancel out 2 of the moles over here. I only want 1 mole in my eventual unit. And I've got dm9 here. I've got to get rid of 6 of those. So I'm going to put dm6 on the top. The only other thing that the rate constant actually always has is a unit of time on the bottom, so that there's also a unit of time on the right-hand side of the equation. So this in red is the overall units of the rate constant. It would probably be written as dm6 moles minus 2 and seconds minus 1. So it's a little bit funny, not that those units really mean anything, they're just there. All the rate constant does, both in number and in units, is really just make it so that the 2 sides are equal, that we can equate rate to concentration, which is going to be really important going forward. But this is how you'd work out the units of the rate constant. To actually solve for the value of the rate constant, you would need to plug in from rate data that you've taken the value for rate and also the values of concentrations that you used in a particular trial. And so you'd actually plug in the values. I should have drawn that arrow down here. If you plug in the values for those, you then just algebraically solve for what the value that K must have at that particular temperature. The most common way you're going to be presented with order of reaction problems is really pretty simple. You'll be shown tables with concentrations of each reactant and the initial rate of reactions. And then you're going to see they're going to vary the concentration of one reactant at a time, and you'll be able to see the effect that has on the overall rate. So when you do these problems, you just compare 2 different trials or 2 different experiments. So I can see that from trial 1 to 2, the concentration of B is not changing, but the concentration of A is being doubled. So this is a good 2 trials to look at, because I'll know that any effect in the rate is happening because of the change in concentration of A. So I can see that doubling the concentration of A led to the rate increasing by 4 times. And so whatever I do to A, it seems like it has a squared effect, or 2 times that effect in this case, but a squared effect on the rate. That implies that A is a 2nd order reactant, because doubling it led to 4 times the reaction rate. I'm going to try to find 2 trials to compare for B. And the best 2 that I can see is from 2 to 3, because the concentration of A stays the same, but the concentration of B doubles. When I do that, when I double the concentration of B, there's actually no effect on the reaction rate, so zero impact. That means that B is a zero-order reactant. And so overall, the rate expression would be rate equals K, and the only thing in our rate expression would end up being A squared. So that's a really ugly looking rate expression, but it does match this data. So B is actually not involved in the rate in any way. It's a zero order reactant, but this is our rate expression. Now if we wanted to solve for K, we could plug in the value for the rate on the left-hand side at 0.002, and we'd plug in 0.5 for A here, 0.5, we'd square 0.5, and then we would solve for the value of K algebraically. We could also solve for its units, but I'll leave that for the sake of time, and we can complete it in class.